connecting your world.
You open your browser, type in youtube.com, and hit enter. In a fraction of a second, your request travels hundreds or even thousands of miles to retrieve a video and bring it to your screen. But before that data can travel across the country, it has a more immediate problem. Right now, your computer is trapped inside a local area network, or LAN. Devices on a local network communicate using Layer 2 of the OSI model, relying on physical MAC addresses and network switches. Those switches find devices by shouting broadcast messages to everyone connected. If we tried to scale that up and make the entire globe one massive LAN, the sheer volume of broadcast traffic would crash the system instantly. To avoid that collapse, we need a different set of rules. We need a system explicitly designed to navigate the spaces between distinct networks. Welcome to Layer 3, the network layer. Down here, your video request is chopped up and packaged into individual units of data called packets. To leave the local network, those packets need a very specific kind of label. While physical MAC addresses are permanently hard-coded into your hardware, Layer 3 relies on logical addressing, IP addresses. An IP address tells the network exactly where you are located in the global topology. This diagram compares our two IP addressing systems. On the left is the older 32-bit IPv4 standard, constrained to roughly 4.3 billion addresses, a pool that is actively overflowing today. On the right is the modern IPv6 standard. It relies on a 128-bit format, expanding the capacity so vastly that it provides a nearly infinite grid of unique addresses for every device on the planet. Armed with its IP address, your packet now looks for the exit door to your local network. In networking terms, this is your default gateway. To successfully hand the data over, your computer uses the ARP protocol. ARP translates the gateway's logical IP address into its physical MAC address. It bridges Layer 3 back to Layer 2 just long enough to make the physical jump across the room. The router accepts the packet. You are officially out of the local broadcast zone and into the calculated mathematics of the global routing matrix. The gateway is a router, or in massive enterprise environments, a highly specialized Layer 3 switch. Devices like this Cisco 7505 are built for ultra-fast hardware-level routing, using dedicated silicon chips to perform IP lookups independent of a standard CPU. The router's primary job is to read the packet's destination IP address, compare it against known paths, and make an intelligent decision on where to forward it next. It makes that split-second decision by consulting its routing table, an internal directory mapping out the most efficient paths to other networks. Network engineers can manually program paths, a process called static routing, which works well for simple setups. Out on the internet, fiber cables get severed and traffic spikes unpredictably. To survive that environment, routers rely on dynamic routing. Dynamic routing protocols allow routers to constantly talk to one another, updating their maps in real time. It is the mathematically viable way to manage an internet that is constantly shifting and rerouting. Your packet drops into the maze of ISP networks. Because different organizations control different sections of the internet, crossing these boundaries requires specific navigation protocols. This diagram shows a network running OSPF, which calculates cost metrics to find the most efficient route within an organization's zones, like Area 0 and 1. Edge routers, ASPRs, act as translators, injecting data from older protocols like RIP or EIGRP into OSPF to cross boundaries. When it's time to leave that local topology and jump between competing massive internet service providers, the handoff is managed by BGP, the Border Gateway Protocol. BGP evaluates the web of business agreements and provider policies to navigate the overarching global backbone. We can track this exact hop-by-hop journey using diagnostic tools like Ping or Traceroute. They utilize a Layer 3 protocol called ICMP to report back on every router the packet encounters, immediately flagging if a link drops. Together, these protocols function invisibly. They identify dead links, compute paths around traffic jams, and cross the country in milliseconds. The packet finally hits the YouTube server. The server processes your request, locates the video data, and fires a stream of response packets back through that exact same Layer 3 gauntlet. In the blink of an eye, the network layer executed its core tasks. It applied logical IP addressing, calculated the optimal mathematical path, and forwarded packets hop to hop. It accomplishes all of this through abstraction. Layer 3 operates entirely independent of the physical hardware. It doesn't care if it's traveling over a copper wire, an undersea fiber optic cable, or a Wi-Fi signal. It focuses solely on end-to-end delivery. Without this architecture, every computer would remain isolated on its own local island, unable to reach beyond the physical cables plugged into its walls. The network layer is the invisible logistics engine that puts the inter in internet, tying billions of separate machines into a single unified globe.
Welcome to TechH FiberNet, connecting your world. Subscribe now.